In this video, I want to find the partial fraction decomposition of a rational expression, this rational expression. But I thought we'd start going the other direction. My goal here is to write this as the sum of three fractions. I thought we'd start by actually adding, going the other direction. So I'm going to do two different examples of adding rational expressions by finding a common denominator. So in this first problem, I would need to multiply the first fraction by x plus 5 squared and the second fraction by x plus 3 to find my common denominator. And so I have a common denominator, so I can go on and add those fractions together. And so on top, I would have 2 times, and I'm going to go on and multiply that out. So that'd be x squared plus 10x plus 25 plus 3x plus 9. All over that common denominator. All right, and finally, I can distribute and combine like terms. So 2x squared. That would be 20x and 3 more gives me 23x. And that'd be 50 and 9 more plus 59 all over that common denominator. So if we were to take this rational expression and do the process of partial fraction decomposition, we'd find these two fractions. So let's do one more example of adding, and then we'll talk about partial fraction decomposition. So now I have 3 fractions to deal with. And I know my goal is to get a common denominator, so instead of writing 3 separate fractions the way I wrote 2 separate fractions here, I'm just going to go on and say they're all going to be over this common denominator. This first fraction I would need to multiply top and bottom by x plus 5 squared. So I'd have 2 times x plus 5 all squared. In the middle, I need 1 more x plus 5 and the x plus 3. So I'd have 1 times x plus 3 times x plus 5. And then finally, I need to multiply this last fraction by x plus 3. And again, I'd have the same denominator, so I just wrote it one time. All right, and then we go through the same process as last time, where I multiply everything out and collect all of my like terms. Go on and pause the video here and do that on your own. And I'm going to count to 3 in my head and then write down an answer right here. After you multiply all this out and combined all of your like terms, you would see 3x squared plus 31x plus 74 all over that common denominator. And what I notice is that these two rational expressions, my answers when I add them, don't look that different. When I do the partial fraction decomposition, this one takes all 3 of these fractions, and apparently this one only takes 2. And the real idea behind this is that I really don't know which case I'm in, but what I know for sure is the only possible combinations of things, fractions I would add together that would end up having a common denominator of x plus 3 times x plus 5 all squared is some number over an x plus 3. I have to have that one. And I'm going to say c over x plus 5 squared. I have to have that one. These two fractions have a common denominator of x plus 3 times x plus 5 all squared. But what I find out here is that I could also have that happening. So in my partial fraction decomposition, I have to include it because something in this form also has a common denominator of x plus 3 times x plus 5 all squared. And the cool thing is when I do the process, I don't know right now whether it's something that looks like this or something that looks more like this, but when I do the partial fraction decomposition process, I will either find that b is a non-zero quantity or 0. If I get b equals 0, then I know I only needed these 2, and that takes care of itself. If I get a different value for b, then I needed all 3 fractions. And so now that I know how to set this up, the idea that I have a non-repeated linear factor, so I need a over x plus 3. And then I have a repeated linear factor, so I need b over x plus 5 and then c over x plus 5 squared. If that was a cube, I'd just keep going until I got to that highest power. But now I can just multiply both sides by the denominator and then set equal the coefficients of my polynomial. So let's do that. If I multiply this side by the denominator, I would just get 2x cubed plus 13x plus 25. Multiplying this through this side, in this first term, the x plus 3's would cancel, and I would get a times x plus 5 all squared, plus, when I multiply the bottom times this, one of the x plus 5's cancel, and I get b times x plus 3 times x plus 5. And then finally, on this last term, x plus 5 squared cancels, and I get c times x plus 3. All right, so on this right-hand side now, I need to multiply some things out, and then we'll talk about combining some like terms. All right, plus, and I've run out of room here, cx plus 3. Being very careful with my parentheses. All right, well, what I would do next is collect the things of the same degree. So I'd imagine multiplying the a through, and I'd imagine multiplying the b through. And what I want to do is kind of shorten my work, because I know I would get ax squared and then plus bx squared, and those are the only things with an x squared. I factor out the x squared, and I get a plus b. And that would tell me that a plus b has to equal 2. So I can do that just by saying, well, ax squared plus bx squared would have to equal 2x squared. So that lets me write down that first equation I'll have, that a plus b has to equal 2. And I'm going to leave a space there because my other equations will have a c in there. I know I'm going to have 3 variables. So now I want to think about things that have just an x term, an x to the first. So I'd have 10ax plus 8bx plus cx. And that's going to have to equal 13x. So that would tell me that 10a plus 8b plus c is equal to 13. And now I just need to think about the constant terms. And here I need to think about distributing again. So I would end up with 25a plus 15b plus 3c. And that has to be equal to 25. And so now I have a system of linear equations on 3 variables to solve. So I'm going to rewrite that system on the next board. A plus b equals 2. 10a plus 8b plus c equals 13. And 25a plus 15b plus 3c equals 25. Now we need to solve that system of linear equations. Since I already have an equation that just has a's and b's in it, I'm going to write that one down, and I'm going to use the second 2 equations to get rid of the variable c. I want to eliminate the c. So I'm going to multiply both sides of this second equation by minus 3. And that way when I'll get to add the equations and eliminate the c's. So distribute a minus 3 through the left-hand side. 13 times minus 3 is minus 39. I'm going to leave this equation alone and just rewrite it over here. Add the 2 equations. Minus 5a minus 9b, the c's canceled by design, is equal to minus 14. I'm going to write that equation on In this system, just with one small change, I'm going to go on and imagine multiplying by -1. 5a plus 9b equals 14. So now I can use this system to finish solving. All right, so I'm going to multiply the top equation by -5. And what I realize now is I could have just written this one down here and multiplied the top equation by +5, but there's always more than one way through one of these problems, so I'm just going to stick with what I've written here. Adding these two equations together, the a's cancel. I'm left with 4b equals 4, so I get that b is equal to 1. Well, I'm told that a plus b has to be 2, so if b is 1, then a is also 1. And now I can use any of the original equations to find c. I'm going to use this original equation, which if I plug in 1 for a would be 10 plus b equals 1, so that would be plus 8 plus c equals 13. So I have 18 plus c equals 13. Taking 18 away from both sides, I have c equals -5. So now I've established the partial fraction decomposition we were searching for. That this original rational expression is equal to, well, a was 1, b was 1, and c was -5, so I can write that as a subtraction. And so I find I really did need this term because b wasn't 0, and this is how I had set up every single one of these partial fraction decomposition problems that only involved linear and repeated linear factors.